This is a presentation of the chapter on steady state error, which we started in class, but unfortunately we couldn't complete. So I'm going to just more recap of what I've covered already and then cover the remaining topics. Now, bear in mind, this chapter is quite lengthy, so we'll be having two separate videos. So I'm going to start here with the first video to cover steady state error, and then the next video will be covering topics like static error constants and dealing with systems with non-unity feedback. Yeah, so yes, let's start this part of the video series. Uh, if you look at this slide here, you'll find the various topics we have to cover to be able to set specification for control systems. So number one, transient response. Number two, stability have already been covered. So number one, transient response, the chapter we saw topics like we've seen percentage overshoot with things like damping ratio, natural frequency, settling time, rise time for second order systems. We've done that, of course, for first order systems as well, but the chapter on second order system is more relevant to us because it covers a more broader type of response we can get from systems. So we're going to see that later, how to approximate high order systems to second order systems. Now, the second number is stability, which we've covered in the last chapter, where we covered topics like analyzing stability using the locational poles on the complex plane, but we've also seen the Ralph-Hurwitz criterion, which allow us to analyze stability of system without explicitly finding the closure poles. Now, this particular chapter, steady state error, is a topic that's going to deal with what error do we get when a system has stabilized, so in a way, when the transient part is finished. Of course, for us to be able to assess steady state error at all, we have to make sure that the system is stable. So number two, their stability is going to be fundamental. So before you even venture into finding the steady state error of a system, we would need to ensure that the system is stable in the first instance. So steady state error, of course, like we said, is when a transient part has died off. So this is why you find here as t goes to infinity, that we're saying the system has stabilized. So three types of inputs to be considered: step, rep, and Western parabola. Now, why is this three inputs? So these are the waveforms for the three inputs. For step, we know how it is, rep, and parabola. Now, what is the physical meaning of choosing a step? This input is that we're trying to see how the system is able to cope with tracking position. So if you want to assess the ability of a control system to track position of a given system, you're going to use a test input, which is step. If you want to assess the ability of a control system to track a body, for example, moving at constant velocity, you're going to use a test signal as rep. If you want to assess the ability of the control system to track a body moving with constant acceleration, you're going to use a parabola as test input. So these are the time domain representation here and the Laplace of these test signals. So we've covered this more or less. So if you look at the third one there, designer must check the system for stability while performing steady state error analysis and design. How would you perform stability analysis? So we've answered that already. You could use the location of poles in the complex plane, or you could use a Ralph-Hurwitz criterion to do that. Now, this is an example of the test signals we talked about. So if you have a tracking system which is located on a given country on Earth, on land, and then just tracking something in space. If you have a geostationary satellite in orbit, then that's an example of a position tracking. So you're going to use a step signal for that to test the ability of a system to track a geostationary orbiting satellite. If you want to assess the ability of this tracking system to follow a satellite orbiting at constant velocity, that's a rep signal. And if you want to assess the stability of a system to track an accelerating missile, of course, constant acceleration, that's a parabolic test input. So it's just an example. You might find those examples in your own areas of application, of course. This is what you just said. You have three test inputs with some descriptive there, so you can just go through that. So for the step, for the rep, and for the parabolic input. Now, what do we mean by steady state error? So if we take this example here for a step signal, So we all recognize input, this is step signal. So if it's a unit step, this is going to be magnitude 1 here. Now, this is your desired input. Yep, and this is how your output is behaving based on the transfer function of the system. So in this case, output 1 here we see as the transient part. So it's the transient part where the output is still changing, has died off. We find output to match exactly the desired input. So in this case, error 0, because output is equal to the input. Now if you look at output number 2 here, so again it's a transient part here, but when the output has stabilized, so there's no more changes, we find that you have a difference between the desired value and the output. But importantly, the system is stabilized. So this error here is fixed. So it means you have a fixed steady state error. So, okay. Now, if we apply a similar scenario to a rep signal, so this is what we get. So again, you have a desired input. So this is your input, which is the rep, means something which is moving with constant acceleration. And then if you look up output 1 here, we find that output 1 is able, over time of course, to reach a state where there's no difference between the input and the output. So here's error is 0. If we look, for example, now another case where output number 2 here again is trying to track the input, and then after some time we find a difference between the input and the output to remain constant, fixed. So it means this system, output number 2, has been able to track the body moving with constant velocity, but it's an error between the two. So this is a case of a constant error. It's a case where there's no error, so it has been able to track it perfectly. This one is able to track it with some error. And this one now, output number 3, is not able to track it. So you can find the error between the input and the output 3 is diverging the time, increasing all the times, ultimately to go to infinity. So this is a case of a system which is not able to track the body moving with constant velocity. So when we'll be assessing steady state error shortly, we'll have these three situations. So error can be 0, can be constant, can go to infinity. Because remember, we're talking of time going to infinity here for steady state error analysis. So important this slide is when we are studying steady state error, we're going to look at two main influence on the steady state error. One is system, means transfer function, and second, the type of input applied. We've seen three types: step, the rep, and the parabola. And they have physical meanings. Very important to keep that in mind. But important is the configuration of the system. What we mean by the configuration of the system is this particular system you're designing or you're considering for a particular task at hand. Is it able to do that task? Is it able to track position? Is it able to track constant velocity? Is it able to track constant acceleration? Now, we do have sensitive errors that can creep in because of non-linear sources like backlash in gears and minimum voltage for a motor, back EMF, and other non-linear sources. But we are not considering this here. We're looking just at configuration of system and type of input. So let's start with steady state error as applied to unity feedback systems. So it's a very common control block diagram where you have a desired input R, you have an output C, and you're feeding back this output to compare it to your desired input, and you have an error signal, and based on this error signal you can control your plant. So important here in this chapter we're studying steady state error. So how is error defined? It's the difference between your reference signal R and your actual output C. So this is fundamental. Always errors need to be defined like this. Now we do know if you have a block diagram like this, you could define a closed loop transfer function T, which is G over 1 plus GH, but in this case here, H is 1, so it's G over 1 plus G. So if you're given your system in a closed loop form, then of course in that block diagram there, if you consider just this part here where T has input R and output is C, you don't find the error. But here in this configuration, you do find the error because you have a summing node. So if you want here to reconstruct error, you would have to add this summing point here where you're taking now the desired input R and subtracting output to get this error signal. So this summing node is not typically found in the formulation of the control system in closed loop configuration. But if you want to generate the error E, in this case where you're given the closed loop form, you would have to add this summing node here. Okay, now in this case, first assignment we have is if you put this configuration of T, how do you find a steady state error? If we start here with this configuration, this equation here is always valid. This one you see it's always valid, is always equal to R minus C. Now, if we want to eliminate C from this formulation, because we want to get the formulation where we just have an input and a system. So this is T and the input is R. So a very simple substitution. We find that when you multiply T with R, you get C. So you can easily replace that C here by TR. And then just with the manipulation here, you just have to factor one R, you get this formulation here. So ultimately, ES is equal to RS into 1 minus TS. Very simple formulation, but this is what we're going to use to find the steady state error. Okay, now if you look at this formulation here, so E infinity means the error when time is going to infinity. So it's a limit as t goes to infinity of ET. So it's a time domain representation. But since we are formulating E in the Laplace domain, we use a final value theorem. So final value theorem is exactly this. If you want to find the steady state value of any function, actually not just error, any function f of t, yep, you just take the limit as t tends to infinity of f of t, and it is equal to the limit as s tends to 0. So time going to infinity corresponds to s going to 0, means no changes, of s f of s. So if you want to find the final value of error, you have to replace, of course, the function by et here. We don't have et, so we use s es. And we just found above that es is actually rs into 1 minus ts when the system is in closed form. You replace that there, so this is the equation we'll be using to find the steady state error. Let's take an example to illustrate this. So if you're given the closed loop form of a control system as follows, and you want to find a steady state error for unit step input, so we're going to apply this equation simply. So in this case, RS is 1 over S. Your RS 1 over S and TS is as given. So ES and then RS is 1 over S and TS is as follows. So your ES, we just say is RS into 1 minus TS. So if you just replace here RS by 1 over S, so this is your 1 over S here, and then just multiply by 1 minus TS. This is what you're getting. So once you found your ES, we apply the final value theorem, which is limit as S tends to 0 of SES. So the S in front of ES is going to cancel with this one, and you replace by 0 now because S tends to 0. So you see 0 is 5 over. This one has cancelled out with S found in SES. 0, 0, so you get 5 and 10, so you get half. So you expect the steady state error to be non-zero in this case. The system is going to be able to track position because it took a step input here, but it will not have a zero steady state error. It would have a steady state error of half or 5. So this is the method you would choose when you're given a formulation of closed form. But more common in this chapter is when you're given a system of this format here, where it's not in given closure form. So you're given your plant here, you have R and C, and naturally in this configuration you would have ES. You don't need to add anything further. So we can easily derive an expression for ES similarly. So E is always equal to R minus C, like we said. So again, the aim is to eliminate the C here. So we get a formulation for the error in terms of input R and the configuration of the system, which is G. So here we know that E times G is equal to C. So we replace that here. We get ES equal to R minus ESGS. So we gain this group terms, and we're able to find ES as equal to RS with 1 plus GS. So very important equation again, which can be derived readily. So we'll be using that a lot now. So we can find in this formulation here, your error is dependent on the type of input you're choosing and the configuration of the system. So let's start here by first analyzing what influence does the input has. So let's consider first, of course, you will apply the final value theorem just like we've done earlier, same formulation. But now ES would not be in terms of T, but now in terms of G, which we just found in the previous slide. So this is straightforward. So next, let's study the versions, the result we'll get when we start applying different types of test inputs. So we say step input is for position. So if you were to replace now this formulation, we had RS in the numerator. So if it's step input, R becomes 1 over S. Okay, so it cancels out here. So you get 1 over 1 plus If you just took yes, it just cancels out. Just 1 over 1 plus gs. Now the 1 in the numerator and the 1 in the denominator here don't have any s, so the limit doesn't apply to them. So the limit just translates to the term here. So the steady state error for step input is 1 over 1 plus limit as that's to 0 of gs. So this is an important term for us to analyze this limit. And of course, this result will depend now on gs because already set the input step. So this limit as s tends to 0 of gs is called the DC gain of forward transfer function. DC gain simply because the frequency is 0. The frequency is 0 as DC. Clearly, this limit would depend on the transfer function g now. Yep, so let's take a closer look at the general form of gs. So you can write any transfer function in this format here, where in the numerator you have a factorized form all the zeros, in the denominator all the factorized form all the poles, and you might get this integral term here, which actually are, if you have 1s, it's a pole at the origin. If you have s squared, it's 2 poles, and so on. So the number of poles you have at the origin is called a type of a system. So if there's no pole at the origin, this is just going to be n is equal to 0, and then s power 0 is 1. And then you just have all the poles in this format here. So this type of system is a fundamental configuration for your system, which will affect steady state error. Let's see how. Now, just before we go there, it's fundamental for us to see that we're going to apply this equation again, and we're studying this limit part here, and what affects this limit as s tends to 0 of gs is a type of the system, is what we're saying. Okay, so let's consider some cases here. Again, this is your general format here. So we're interested in the system type as we have a critical influence of the limit of gs that we want to find. Let's see how what different system type means values of n. So let's say you want to study steady state error we'll get for a type 0 system means n is 0. So we're replacing here n by 0. So we want to find limit as s tends to 0 of gs. Now we've seen in the previous slide. So if you replace s by 0 here, so you get 0, 0. If you replace s by 0, you get z1, z2 in the numerator. In the denominator, since the type 0 system, we get s power 0. And then here, because s is 0, we get p1 and p2. So this is not equal to 1, it means we get a constant. So when this limit is a constant, so we replace now in our equation for the steady state error, we get 1 over 1 plus limit as s tends to of gs, and this part here we got a constant for type 0 system. So we get this 1 over 1 plus k is not a constant, means non-zero. So what can we conclude therefore? A system of type 0 will be able to track position for sure, but with non-zero steady state error. So if we just go back a few slides, this is remember we saw some graphs there. So this is the case you are getting here. So we have an input step. Our output, you will have a constant steady state error. Okay, so done. Now, if we decide if we had a system which is of type 1, means n is equal to 1 now, so same type of analysis, limit as s tends to of gs now. If you look at this one here, so this is going to be n is equal to 1, but all other terms are the same. So when s tends to get z1, z2 in the numerator, in the denominator p1, p2, but you do have an s power 1 now in the denominator. So when you replace s by 0 here, you have a 0 here, so you get infinity for that limit term. It means now your steady state error, which was 1 over 1 plus limit as s tends to 0 of gs, becomes 1 over 1 plus infinity. So you get a 0 because 1 over 1 plus infinity is simply infinity. So 1 infinity is 0. So in this case, a system of type 1 will be able to track position with a 0 steady state error. It's going to be exactly matching your input. Now you can imagine here what actually caused this system to have 0 steady state error is because of an s term in the denominator which produces 0. So if this was of a type 2 system, you have s squared, it produces 0 here. This is what we're saying, actually a system of type 1 or higher will be able to track position with 0 steady state error. So main conclusion here is if you want to track position, your system should be at least type 1 to have 0 steady state error. If it is of type 0, you would have a constant steady state error, but still you should be able to track position. Now, next, we follow a very similar methodology now. We consider rep input, which corresponds to tracking a body with constant velocity. So this equation here is standard. We've been using that for step. Now RS, of course, is going to be 1 over s squared. So 1 over s is going to be cancelled out. Then the s is going, the remaining s here will go in the denominator. So we get this term here, s plus sgs. If you just multiply s by these two terms here. Now as limit, of course, as s tends to 0, this s is just going to become 0. So this is what remains back. So the steady state error is now 1 over limit as s tends to 0 of sgs. Remember when we were dealing with a step input, the term was a bit different here. We had 1 over 1 plus limit as s tends to 0 of gs only. Now we're getting sgs. sgs. So this is the limit term we have to study. So it's sgs now. So we take a similar approach. We again consider general form of your system. We have already set this input to be rep. So let's start with type 0 system. If we find this limit here, yep. So remember you have SGS. This is why this S is there. Now it's a type 0 system. So this is S power 0 here. So there's nothing in the denominator. 0s in the numerator because it's SGS now would create a 0 result. And now the steady state error, if you just go one slide back, was 1 over that limit. So 1 over 0 gets infinity. So your steady state error now would be infinity, meaning a type 0 system is not able to track constant velocity moving objects. Interesting. Now, if we were to consider now a type 1 system, so same analysis, except that, of course, the denominator now I have s power 1 because type is 1. So this cancels out. This s here is cancelled out by s. So now you get a constant term. And just like we see earlier, so the steady state error is 1 over that limit. So 1 over k, you get a constant. It means now a type 1 system is able to track a body moving with constant velocity, but with a non-zero steady state error. You have a constant error in your final steady state. Okay. If we increase now type 2, as you could imagine, now you have s squared in the denominator, you have an s here, so this s cancels 1, but you have an s remaining in the denominator, which when you put 0, because the limit of s tends to 0, get infinity. When you replace that limit now with infinity in your steady state term, you get 0. So what we're finding here is a system of type 2, and of course higher, will be able to track constant velocity with a 0 steady state error. So let's complete analysis of third type of test signal, named the parabolic input representing bodies with their constant acceleration. So again, this term is there. So we're using the same term we've been using for other type of inputs, but instead now RS is going to be 1 over s cubed now. So you have an s squared left behind, which goes in the denominator. When we replace s by 0, this term goes away. So now we have to find 1 over limit as s tends to 0 s squared gs. Okay, so we need to study this limit here and maybe some inferred system types that would lead to infinite constant and zero steady state error, but let's look at the analysis formally. But you've seen the trend there based on the step and the rep parabolic, you can infer the trend. So if we were now to consider for a parabolic input, so this is what we said, you have to analyze this limit s squared here. So if you have a type 0 system, you have s squared top, 1 in the denominator, so you can get 0. So infinity means, as expected, a type 0 system is not able to track acceleration. It was not able to track constant velocity, so definitely it's not going to be able to track constant acceleration. So that's expected. Now, if you increase the type to 1, we find that even there, you had an s squared in the numerator from the s squared here, but now it's type 1, so you have s1 here, and you get an s remaining in the numerator. When you put that to 0, it gets 0. 1 over the limit gives infinity. So again, a system of type 1 also cannot track constant acceleration. If you put a type 2 system now, you have s squared coming from here, but you have s squared from the type of a system, and these s squared cancels out, so you get a constant. So now the steady state error is a constant. So we find a system of type 2 can track a constant acceleration body, but with a non-zero steady state error. And as you'll be able to infer, if you were to choose a type 3 system now, so s cubed in the denominator, s squared from the limit term, and s is remaining in the denominator. If you put that to 0, you get infinity. Now the steady state error becomes 0. Therefore, to be able to track constant acceleration body, you need at least a type-free system, control system. That's very clear now. Okay, so let's look at some work example now of how to apply this. Let's take a control system as shown here. So we have to find a steady state error for inputs of 5 step, 5t ut. This one will be ramp, and 5t squared ut is going to be parabola. And of course, ut is a unit step function. So if you want to solve that based on the equations we've seen earlier, okay. So the steady state error for step, we've shown that already. Yep. So this term had been derived already, and now we just have to plug back. Of course, when you had unit step, that was 1 over s. This is why you have 1. Of course, if you just go back one side back, so now it is 5 times the step. So you're getting a 5 on top here. Just replace the limit out of gs as s tends to 0. If you do that limit here, you're going to get 120 times 2 here over 3 times 4. So if you work this out, you're going to get 20. So again, 120 times 2 over 3 times 4 here, so you get 12, and then 120, you get 12, you get 10 times 2, you get 20 here. So your steady state error is 5 over 21. If we work it now for a ramp, so again, same comment, we've chosen 1 over s squared here for unit ramp, but now since it's 5 times the ramp, so you have 5 coming in the numerator here. And then you have to work out the limit as s tends to 0 SGS. Yep, and we've seen that already. As expected, it's a type 0 system, so you expect the steady state error for ramp to be infinity. So if you were to work this out, the limit as s tends to 0 SGS, so you have an s coming here. As you replace s by 0, all these terms, of course, going to get values, but the s here is going to lead to 0, which is here, so you get infinity. So the steady state error will be infinity. Same comment for parabola, but just one comment here. You have 10 here instead of 5, because if you look at the expression for the parabola, if it's half, this was created with 10 there instead of 5. The same comment as for the ramp signal in the previous slide. You expect to get a 0 here. Infinity means your system, which is type 0, cannot track a constant acceleration system. Yeah. So with this work example here, we stop. So I'm going to continue with another video of continue on this chapter. But till now, I hope you're able to work. This is the work example we'll take up next in the next video session. But till now, I hope you have got a good grasp of the principles discussed on steady state error, and you can now build on that. And hopefully next time we'll be finishing this chapter with more new topics. So we have to look further onto steady state errors, but you have topics like the static error constants to look at, and also what type of analysis where the feedback path here is not unity. When you have a measurement system, a classification here, how do you deal with that? So we'll take up in the